Okay, let's begin. Last time we were counting. Let us continue. 2 more examples to get through on the handout. We are on problems 7 and 8. So let's just ease into it by doing part A again. So dealt 5 cards. How many possible 5-card hands can you get? That was the question, and the answer was because order does not matter. Only the set of cards that you get. So this was just us counting sets. So we have a set of cards, there are 52 things in that set, and I want to choose a subset of that set with 5 things in it. Choosing sets from sets means using combinations. Should is a strong word, can be used. There are sometimes we can use either or, and I'll do some examples of that, but one is definitely more efficient than the other. You're in a situation where order does not matter, you only care about a collection of things. Combination is what you're going to do. So we want to choose 5 objects from 52. Without order or repetition. This means there are 52, choose 5. That's, the notation is literally read that way. 52, choose 5 possibilities. And chances are you plug in 52 in your calculator, you'll find the NCR button, you press that, then you plug in 5, and you press enter, and we got something that was 2 million something, 2 million what?
2,598,000.
So that was the possible number of things, and I think we actually saw that you could play poker once a day for like 10 years and never get the same hand. And given that, multiply that by a bunch of people at a poker table and the possible arrangements where the hands can switch places, and you could play poker your entire life with a bunch of people and never have the same game played twice. There's a lot of combinations. So now we were moving on to B, where we wanted the number of full houses. How many of these hands are full houses? Now, full houses, remember, this is 2 of a kind and 3 of a kind. So an example of such a hand will be 1, 2, 3, 4, 5. I forgot what we said, but I think it was king, king. Doesn't really matter actually. And say a 3, 3, 3. If you have a hand like that, we say you have a full house. How many ways could you get a full house out of that 2,500,000 plus thousand? Well, we want to remember that there were 13 kinds and 4 suits. So we could have the A's. 2, the 3, the 4, the 5, the 6, the 7, the 8, the 9, the 10. You don't have to write this out every time you're doing a card problem, but just to visualize. Jack, Queen, King. So there are 13 kinds, each has 4 suits. So you could be a heart, or you could be a club, or you could be a spade, or you could be diamonds. And you have 4 in each of these, so that gave you 52 total cards, not counting the joker. So, now we ended up with the situation. How is it that we're going to get a hand like this? So, suggestions. Yeah?
So your first card, there's 52 possibilities.
Okay. So, okay, boom, boom. So what do you want to do here?
So it's 52 in the first slot. And
Okay.
then the next two would be 1 because it has to be the same, like, it would be 3 because they're
So you can pick any of the 52, but then there will be only 3 that would go along with. Okay, and then?
And then the next one would be 2 because there's only 2 remaining that can go along.
Why 2?
Because you've already taken up 2 cards.
Okay.
And then there are 2 remaining.
Yeah, but why would I choose that too? Why would I choose from those? Because once I have the 2 of the same thing, I want to get 3 of something else.
Oh, I was doing the 3 first and then...
Oh, you're doing the 3 through 3 first?
Yeah.
Okay, so then 2. Okay, and then what?
And
By the way, we're counting number of choices here. And then?
And then there are 47 cards you can choose from.
How many did we have before? 52?
52.
So, but do we want all 47? Like how many would be out of play now?
3 would be out. 4 would be out of play.
4. So you can choose from among the others. So how much is going along with this reason?
But there will be 48 cards that
48. And once you pick one of those,
there's 3.
yes.
And you multiply.
Now that's a valiant effort. It's wrong though. But it presents a very valuable lesson. What is the issue here? I do agree that it makes a lot of intuitive sense to do this, which is why I want to actually talk about why this wouldn't be the thing you want to do. Do you see what the issue is?
Well, if the dealers do hand out cards that are all dealing to other people, it's not just all to your ones.
No, pretend it's just you. Pretend, yeah, you're playing poker by yourself. It's just you and the dealer. What do you think would be the issue? Yeah?
Is it because we're not replacing the cards?
No. It's something even more elementary, but it's easy to sneak under the radar if you're not paying attention. Because how were we counting before? When we used a combination to count the hands, right? So what does this mean? What are the restrictions of using that kind of logic? Huh?
Just means order doesn't matter, doesn't count.
No order, no repetition, right? Okay, now, this is the framework that we're thinking in. Now, what did we assume with this kind of reasoning? Oh, we can get any of the 52 first. Once we do that, then next we can do blah, then next we can do blah. You literally just thought through picking these hands in order. We're not considering order, right? That is a very easy mistake to make, and it feels intuitive. It feels like you're doing the right thing. But yeah, You just counted all the hands without order, but now you're picking a hand in a particular order, right? This would be the number of ways to probably get a particular full house in a particular order, then yeah, if that was the question. But that's not the question. We want to do this in a way that does not matter, or does not count order. So I don't necessarily want to think of a first or a second necessarily. I do want to think in terms of combinations, thinking of groups of things that I can choose from other groups of things in this way. So that's the first thing. I was going to do another example where I was going to make this kind of mistake on purpose and ask you why, but it's already showing up. This is good. Okay. So let's look at this another way. So now we will use the multiplication rule, so that wasn't the thing that was off. But making sure we're not choosing in such a way that order matters. So now, when it comes to that, we are going to want to dissect things, but you're not necessarily thinking of them as coming one before the other. So what we will do is note we need to choose the parents and the children. So we do need to dissect things here. There is something different about the cards in this hand. These two here, and again, these don't have to come in the same order. You could have the three here and then the king there. It doesn't matter. But I just wrote it this way so that I can group things easier, so you can see them. So these here, these are called the parents. The kinds of cards that are two of a kind would be the parents, and these are the children. Now, ultimately, what you want to do is find a way that you can pick the parents, not in any particular order, and then choose the children, not in any particular order. You multiply both of these numbers together, that is applying the multiplication rule, and that's going to be your answer. So let's focus on one at a time, which neither is first or second, but choosing the parents. Let's focus on choosing the parents. How would you choose the parents?
4 choose 2 times 13.
Okay, explain your reason.
Our reasoning is that, so there's 13 types of cards.
Yeah.
And for each of those types, you can choose, for choosing the parents, you can choose any combination of 2 of those cards.
Yeah. So to illustrate your point, let's get a little bit more specific with the cards that we're picking. Let's say, for example, we pick a king of hearts, and then, not necessarily, and then king of diamonds, but this is the group of cards that are in your hands. Say 3 of diamonds, 3 of hearts, 3 of spades. Okay. So now you decide to choose kinds. How do we choose the kind? So that's like you choosing the K, right? And how many ways could you choose that?
There's 13 ways because there's 13 kinds of cards.
Right. There's a set of 13 things here. I want to pick one of them. For example, the K. There's going to be 13 choose one ways to pick the kind. Pick the kind. Right? Now me using a combination is saying I don't care what order I pick it in, just out of 13 things, choose one of them. There are going to be 13 ways to do that. But now, after I pick the kind, I need to pick the suit. I know I'm picking a K, but which one of the Ks? So what I'm going to do here is via the multiplication rule, pick the suit. And how do we do that?
So then before you choose 2.
Right, there are 4 suits, the hearts, the diamonds, the clubs, the spades. Out of these 4, I need 2 of them. For example, a heart and a diamond. So out of the 4 possibilities, I need 2 of those possibilities. And this is me choosing the parents. Choosing them via combinations to ensure that my order is not going to matter. Then you kind of go and do the same thing. Choose the children. Now that we actually went through on how to choose the parents, maybe someone else can tell me how to choose the children. What, following this same logic, how would I pick the children? Yeah.
12 choose 1 times.
12 choose 1, explain why.
Well, there's one kind that's already taken up by the parents.
Right.
You can't
So
choose that.
if the K was already chosen, now there are 12 things that I can choose one from. So here I'm choosing kind.
Then picking the suit is the same way, except there are 3. You can choose 3, so 4 choose 3.
4 choose 3. Now again, there'll be 4 possibilities that once I choose the kind, let's say for example I pick a 3, there are 4 suits of 3s. I want 3 of the suits. So out of the 4 suits, I'm going to pick 3 of them. Just choose the suits. So I now know how to pick the parents, and I know how to pick the children. In no particular order, because I'm using combinations. Now, for every pair of parents that I could pick, I can pick this many children. The multiplication was going to tell me, since this is the number of options for one stage of your choice, which is picking the parents, this is the number of options for the second stage, or not the second stage, the other stage of your choice. This is how many ways you can pick the children. How many total ways for the entire experiment to go is the product of these two numbers. Gives total number of full houses is going to be equal to 13 choose 1, 4 choose 2. That's how many ways you can pick the parents. That's one stage of the experiment. 12 choose 1, 4 choose 3. That's how many ways I can pick the children. Another stage of the experiment. Multiplying these will give me the total number. So you multiply those. So 13 choose 1 is just 13. 12 choose 1 is just 12. 3,000? Only about 3,800 ways out of the 2.5 million plus. Yeah.
Okay, so what if you choose the children first?
It wouldn't matter. Like I would have written this set of numbers, I would have chosen this and that would have swapped places.
Oh.
But I'm multiplying them together anyway. Right, like if I chose the children first, I'd have 13 choose 1, 4 choose 3.
Yeah.
Then I come over here, I'd have, oh, now 12 choose 1, 4 choose 2. Ultimately, I end up with the same thing. Bonus round. What is the probability of getting a full house? Now we'll talk about probability in more detail starting after problem 8, but we kind of introduced the idea a little bit before, so what would this be?
Is it about 0.144% chance?
Yeah, but how would I get to that number?
Divide the total number of full houses by the total.
Right, I'm going to do this, 3, 7, 4, 4. That's how many hands are full houses out of the total 2, 5, 9, 8, 9, 16. Is that it?
Yeah, that's it.
So that is
It's a 0.00144.
0.00145.
44.
Okay, so that's like 0.14%. In other words, if what just happened, that someone giving you 5 cards, if that happened 10,000 times, roughly 14 of those times, you would get a full house. And when it comes to poker hands, why does one hand actually beat another is actually a matter of probability, right? When someone says, my hand is better than yours, I would win the pot. The reason they win is because their probability, the chances of them getting that hand is much smaller than yours. So you can actually do this for all the different kinds of poker hands and compute all the probabilities, and Wikipedia has a great article on where they literally, in a table, they list all the poker hands, list all the probabilities. What you can do is you can, to practice this problem a little bit more, you can just go and try to actually compute these by yourself and then just look at the Wikipedia article, see if you're right.
Well, Professor Smith gambling, you really must live on the edge.
Huh? No, it's math. I never said
Such a
that I
corrupting
went out and
influence.
did anything, but yeah, you can actually compute these. Now, to be fair, this kind of probability problem, I know we're doing it now at the beginning, but it would be a medium to hard level problem. Like the average probability problem is not going to be this hard in this class. But it really showcases how you have to think carefully, how you dissect things apart. It kind of shows the kind of spatial reasoning that you need for this kind of thing. Let's move on to problem 8. See what you've learned. Okay, so you have 10 balls that are labeled and put in a box. Okay, you throw them in a box, shake up the box. You pick 5 of them randomly without replacement, so once you pick one, you do not put it back. And then you pick another one, then you pick another one, then you pick another one. How many possible scenarios are there of this kind? So mix up, choose 5 at random without replacement. Okay. The second of the 5 is an 8. How many ways could that happen? If you were to do this like a how is it as means like how would you go about doing that? How would you set this up? Yeah.
First, I would do the first step, which is trying the first ball. It's a 9 out of 10 chance that it's not an 8. And then the second step I would do, it's 1 out of 9 remaining balls you have left that could be an 8, and then multiply those together. Which is 1 out of 10.
1 out of 10, like. But that's not. It seems like you're kind of doing a probability, I think. Or no?
Oh, yeah.
No, I just want the number of ways. We're not even dividing out of the total. Like, how many ways could this happen? How would you start by setting this up? How would you? Yeah?
Well, as for the first part, there's 9 ways that it won't be an 8.
Okay.
And for the second one, there's 8 more ways that, I think there's 8 ways that it won't be an 8 then. I mean, not 8 ways, sorry. Yeah, it's just gonna be 9 ways, right?
Let's see. First of all, you want to think of this in terms of combinations or permutations?
Combinations.
I probably think permutations. Why? Because seems to be some kind of inherent order here, right? There are numbers 1 through 10. And I can think of it as me picking something first, and then it mentions also the second of the choices. So order matters. Which means I'm not necessarily going to think of combinations here. What I would think of is number of ways to choose tuples. Once I am thinking number of ways to choose tuples, now I'm going to think of positions in a certain order. Now I'm going to think there is a first position, and a second position, and a third position, and a fourth position, and a fifth position. I want one particular kind of scenario where the second position is an 8, which means how many choices do I have for the second position?
One.
Huh? There's one choice. It has to be 8. So there's only one possible thing that can go into the second position. Now I'm worried about all the other positions. How many possible things could I choose in the first position? It would be 9, right? Because there are 10 things. 1 is off the table because I already know that's going in position 2. So there are 9 other things that I could have put in position 1. Now once I'm at the third position, what are the options? Right, because I would have, the 8 is already picked, and I would have picked someone else. So now there are 8 left. And if I pick someone else, now there are 7 left. If I pick someone else, now there are 3 left. In other words, exactly the same way we started the last problem is how you would do this one. And the reason why you would choose one over the other is because order. 6. Why did I go
Is he crossed off?
Cross off.
I crossed. Yeah, that's how it happens. Yeah. So, and now we just apply the multiplication rule. So the multiplication rule is a general principle, remember. So it applies whether I'm in the situation of order or without order. Once I can think of things in stages or chunks or pieces, and I want to find the total number of things, I can just multiply them. So it's 9 times 8 times 7 times 6. 3,024 ways. Now remember when we were counting tuples and we were figuring out the P and R formula and all that stuff, we actually did it this way. We actually did the dashes and we counted how many things we had in each dash. That being said, you could have thought of this directly as permutations. So let me kind of stay with that. Note. How? Second is 8. Choice made for us. Doing like a telegram. Choice made for it. They have to. So this means we need to choose how many? Ultimately, we need to choose 4 more because it's a total. We have to choose 5. Right? Now. Order matters. I know I need to pick 4. How many options would I have if 1 is already chosen for me? 9. So now it's just a matter of how many ways can I choose 4 things out of 9 things in a certain order? That's P94. And if you calculate that, that's actually that. So you could also think of it that way. Because here, the moment they start saying second, first, third, blah, 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 order matters, now you stop thinking combinations, start thinking permutations. And there's always the danger of mixing the two, which is like what happened in the last problem. We chose the hands with combinations, but then we went like this when we were choosing the full house. Once you mix and match the permutation and combination, that's when things go wrong. And it's very hard to realize when you're doing this because it would feel so intuitive to actually set it out this way. But you have to just be careful. Know that order matters or not first. That dictates everything else you do afterwards. Know if there's order, know if repeats can happen. That will dictate everything else you do. Every other thought you have, can I choose it in this way in like a certain order in stages? Do I have to use combinations? Can I use permutations? That's all chosen before you even start the problem. And there are times when the problem itself won't have inherent order, but you might put a fake order on it yourself to get the problem to work out. And a lot of times that also works out as well. But yeah, you could have thought of this directly as a permutation idea, or just actually do the stages, the first stage and the second stage and the third stage. The part B. The second of the 5, so B. And again, order matters here. The second of the 5 is larger than the first. Okay. So how many ways can I draw these guys so that the second thing I draw is going to be larger than the first thing I drew? So then, I guess we can just, we're thinking in a certain order, so we do the first position, the second position, the third position, fourth position. Okay, what happens?
First one will be 9, because you choose a 10, and there's something larger than that. So you have to choose one of those 9.
Okay, so one option is you choose a 9 first, and then the second would have to be a 10, right? Now these account for one choice each, right? So this is a one choice. This is one choice. What about the rest?
Multiply those 2 by 8, or 8p.
Yeah, 8p3 pretty much, or 8, 7 times 6, which is actually equivalent to 8p3, right? 3 factors of 8 counting down in multiplication. So you have 8 times 7 times 6 choices there, which I believe, did we compute that? No, we didn't. It's the same as 3024 divided by 9. How many choices is that? $136 choices. 336. Okay. Is that the only scenario? No. So, or what else could I have?
A, you can choose 9 over 10.
Huh?
The first number is 8, then you can choose 9 over 10.
So if the first number is 8, you would have 2 choices here.
So do you have to just go down one by one?
Just gonna get like 1 choice, 2 choices, 3 choices.
Huh?
You're just gonna get 1 more choice for each number that you put in.
Yeah, so how do we finish? What would be the last 3?
It's the same thing.
It would be the same 8, 7, 6, right? Now, of course, you do this 1, 2, 3, 4, 5. You're going to notice a pattern happening. There is a possibility of the 7 being in the front, in which case you will have 3 choices, in which case you would end up with 8, 7, 6 choices. Now, clearly you're seeing a pattern here. This is going to go all the way down to when is it going to stop?
The first number is 1.
It'll go all the way down, and then pretty much any choice here, 9 times 8 will go. So you see here, these guys are, this here is really 1 choice, that here is root. So it's 1, then 2, then 3, then 4, but the tail 876 is always the same. So you don't have to write it all out. Hopefully after filling in a few of them, you'll be able to see the pattern that's happening. So, and we also remember from last time that the OR, the exclusive OR, is just you add them together. So this means that the number of ways is going to be 8 times 7 times 6 times, well, the 1 plus the 2 plus the 3 plus the 4 plus the 5. Because you literally have 1 times 876, then 2 times 876, then 3 times 876, then 4 times 876, etc. Right? So remember that little Gauss taught us how to add that up. So that's 9 times 9 plus 1 all over 2. So that's 8 times 7 times 6 times 5 times 9 all over 2. What's that? $735. 735. Now, by the way, what was the total number of ways this could have gone? Well, 10 times 9 times 6 times 5 times 4 and 9. 10 times 9 times 8 times 7 times 6. And if you multiply that out, that's the total number of ways it could happen. How many ways could it happen where the second one is larger than the first? 735.
I think that's right.
That doesn't make sense. It's like even the third one, 3 times 336 is bigger than 35.
What?
Like that makes. I mean, even by the second option, like 336 plus 2 times 336 is already bigger than 735.
Yeah, 735 is just not the right number.
It's
Oh, I got it.
7560.
Okay. Do we agree?
Yeah, that's right.
Okay. Yes.
How do you know when it's the lower and when it's like when you have
Oh, I'll tell you the specific instances, but I did mention this specific instance here. It is an exclusive OR because none of these things overlap. For exclusive OR, you add. So if something can happen this way or that way or that way, and there's no overlapping, you just add the number of ways for each. Yeah.
So we like identify problems like this without having to like list through all of the steps and really see a pattern.
Identify in what sense?
Like that they have this pattern where you just add up number, you know, like times.
No, I wouldn't really think there's a general way for that. Sometimes it's nice to set things out. Yeah.
Where's the 5 coming from?
Oh, I can't. I did this.
So wouldn't the 5 not be in the numerator since it's like 10 over 2? And that
So the 2 shouldn't be there. The 5 should be there. The 2 cancels into the 10, leaves me with 5. That 5 is here. The 9 is here. 8, 7, 6. So it's actually double this.
Yeah, that's right.
Multiply that by 2.
15,000.
That
Just wanted to try.
Yeah, I just cheated here. We did that thing where we add things and remember when we had the 1 plus, this was a long time ago. all the way up to n, and then you just added it backwards. And then when you add both of them, you had n times n plus 1, and then because you added it twice, you have to divide by 2. That's the sum of the first n integers. You don't have to know that, but that's what I used. So if I add up the first 9 integers, the 9 positive integers, it's going to be n times n plus 1 over 2, where n is 9. And so it's going to be that. But you could have just done that. Okay, that does that. Let us move on to... Well, I want to move on to probability now, but I need to mention some preliminary. So before we move on to the probability thing, let's mention some preliminaries. Yes.
No, so just the answer to number part B for number 8, so that's the same as doing like 9 choose 5 for like a permutation. So is that just like a coincidence, or is that just a coincidence, or like can you think about the problem in terms of just like permutations?
I would say it's a coincidence here. How do you think of that in permutation? That it's just P95, P95. I don't know, I think that's just a coincidence. At least I can't see a way that that's the way I would have thought of the problem. Like, I didn't know it at the beginning. But the other way made intuitive sense though, the part A, preliminaries. So I just want to introduce a new term. Let's say A, B are sets. We say A and B are disjoint. So I'm introducing the word disjoint. That's going to be important if A intersect B is the empty set. So basically, if I were to draw the Venn diagram, the A and the B would be completely separate. They're disjoint. They're not joined together. So we call this disjoint sets. I mentioned these other things to you guys already, so I think we can actually jump right into it. Let's talk about probability. Let's start with some definitions. A random experiment. So, there is something called a random experiment. What is a random experiment? It is a process whose outcome cannot be predetermined. Exactly. So, flipping a coin is a random experiment. Shuffling a deck of cards and picking something without looking at it, random experiment. Sure, I can talk about the possibilities, but I can't say for sure what's going to happen. Like, I don't know that if I flip a coin right now, it's going to land on heads. Don't know for sure. Sure, it could be heads or tails, but a random experiment means you cannot predict the outcome with certainty. And as you may have noticed in life, pretty much everything is a random experiment. No one can tell the future. Probability is math's attempt to kind of make the uncertain a little bit more certain. So that's what a random experiment is. Let's call it define something else. There's something that we call a sample space. I do say A because it's not unique. There are multiple ways to conceive of a sample space of a random experiment. But a sample space of a random experiment is a set of all possible outcomes of the experiment. The elements of a sample space. So all the members in the sample space are called sample points. Definition. An event. So when we say an event has occurred, an event has happened, abstractly in mathematics, what we mean is a subset of the sample space. So remember what subset means? Now, probability. Seeks to measure the likelihood of events in a random experiment. So there's a random experiment. There's a bunch of things in a set, and any of those things can happen at the same time, but I can't predict which one is going to happen. Each of these things are called a sample point. If I collect a group of these things together, I call that an event, and probability is trying to figure out what are the chances of this group of things happening. I should say set of things. Group is technically a technical term. So our definition is going to be the following. We are focused on finite probability. Other kinds of probabilities are different. Let S be a sample space. And let A be an event in the sample space. And suppose all sample points are equally likely, meaning any member of the sample space has an equal chance of being chosen at random. All sample points are equally likely. We define the probability of A by this. P of A is given by the size of the set A divided by the size of the set S. This ratio is called the probability of the event. Example. Flip a fair coin. What's the probability? Of getting heads. So, what you would do is you would think of what would be the sample space for this experiment. Well, possibilities are H and T. These are the set of all things that can happen, right? The coin is either going to land on heads or tails. My event A is going to be a subset of that. So I'm going to choose the things in that constitute the event A. This will only be one event, one sample point, that is H. So what you would do is you would notice that the size of S is 2, the size of A is 1. So this means the probability of A, the probability of getting ahead, is the size of A over the size of S equals 1 over 2. We define the probability of such an event to be a half. Now I do understand this seems very rigorous and too abstract to think about, and this is a very simple problem. Most people won't actually think about it this way. When the problems get more complicated, this is kind of the way you're going to want to think. You're going to want to be able to think about what the possibilities would look like in your mind. And you may or may not be able to list them all. There might be a lot. Like if S is the all possible 5-card poker hands, you're not going to be able to list all 2 million of them. But you have to have some idea of what that set would look like. And you are then going to choose what would the event you want looks like. So for example, all possible full houses. What would that set look like? Then you're going to try to figure out how to count how many things are in one set, count how many things are in the other set, and you divide them in this order, and that is a probability. So counting is going to be very important. What else do I want to mention? Okay, told you that, 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 told you that. Okay, let's mention something called the axioms of probability. Now these things are going to kind of line up with my definition very nicely, but strictly speaking, these aren't things that can be proven. An axiom is just a mathematical fact that we accept on faith. I know that sounds weird to people, but in fact, math is built on faith. There are just a bunch of things that we don't know how to prove that we just say, let's pretend it's true and let's build everything from that. These are some axioms that probability will be built from. One, probability of an event A is a real number, such that you will get a value between 0 and 1 inclusive. So you can't have a negative probability, at least not for us. If you're doing quantum physics, it's possible. But for us, it will always be a number between 0 and 1 inclusive. So if you told me, oh, you did a problem, you tell me the probability is 7, I would know you have no idea what you're talking about. Probability is minus a half. No, impossible. You can't have that. That's not an answer. And you should know that that can't be the answer. Your answer will always be between 0 and 1 inclusive. You can think of 0 as 0% chance and 1 as 100% chance. You can't be, you know what, this is more than certain to happen. Like, you can't really say that. It doesn't really make sense for us. So we're going to assume that that is always the case. One thing you can note is by the definition, if I look at the empty event, right, what are the chances that none of these things are going to happen? Well, that would be the size of the empty set over the size of the sample space. Well, that's 0. So that's how you can potentially get a 0. Right? If the subset of the thing that you're looking for doesn't exist in the sample space, you just say, well, I'm finding the probability of nothing. Versus, if you want the probability of the entire space, well, that's just going to be, by our definition, the size of the set over the size of the set, which is going to be 1. So the probability that somebody in the sample space is going to happen, that probability is 1. In fact, that is the second axiom. The probability of the entire sample space is assumed to be 1. The third axiom. We are going to make the assumption that by adding up, and this, the reasoning behind this is kind of like that, but again, it's not a proof, it's just something that makes sense for our definition. If I have several events, like here's one event, union, another event, union, dot, 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 union. So if I have n events, this or, and I want to find the probability of this or that or that or that or that, then this is going to be equal to the sum of the probabilities. With one caveat. This is called pairwise disjoint, but let's write it out a little bit. If each AI is disjoint from all others. In other words, this is an exclusive OR. These sets are assumed to not have any overlaps. That is it. Every rule that we develop from now on must obey these three principles. Anything that contradicts these principles is deemed false. This is what our universe is going to be based on, the definition and these three principles. At any given time, these have to hold. Let's talk about the law of disjunction, I think I want to mention. And you can kind of see why we would want this to make sense to us. Huh? Can you copy it? I'm not sure we'll get to any more examples, but I'll just tell you a bunch of formulas that we want to be able to use. Think you're good?
Yes.
Formulas that we want to be able to use. And starting next class, we'll jump right in and start using them. It's a very important rule. This states the probability of a union of events, right? Where you don't necessarily know anything about the sets in the union. They could overlap, they might not overlap, but it will always be the probability of the first event plus the probability of the second event minus the probability of both events happening at the same time. And you might say, well, why is that? Well, by our definition, the probability of A union B is going to be the size of A union B divided by the size of the sample space. This is equal to A, size of A, plus the size of B, minus the size of A intersect B, all over S. And this is by the inclusion-exclusion principle, which I mentioned a couple classes ago. We kind of use Venn diagrams to illustrate why it would be true that the size of the union is going to be the size of both sets minus what's intersecting, what's in the intersection. That is going to be the size of A over the size of S. If we just do the arithmetic here, size of B over the size of S, you can split a fraction across the denominator, and across the numerator, sorry, never across the denominator. Okay. And then this, by definition, the size of A over the size of the sample space, that by definition is the probability of A. Size of B over the size of the sample space, that by definition is probability of B, minus the size of the intersection of the size of the sample space, that by definition is the probability of the intersection. So this equation is true. It is an important equation to know. So put it in a box. This is just something we know now. This is a fact. I want the probability of a union, then that's how I would do it. What you can notice here is that if A and B are disjoint, if they don't overlap, then the intersection is the empty set, and then this thing won't be there, and then the probability of the union is just the sum of the probabilities, like in axiom 3, right? But assuming that there's possibly an intersection, you have to subtract all the overlaps. So with two sets, that's how you get the subtraction of the overlaps. So that is the law of disjunction. There is also another important fact that this is going to be very useful. Recall or note. If you look at the universal set, you can write it as any set union its complement. Right? This is a fact that we can see from sets. Here's A, here's the universal set. Everything in here is A, everything out here is a complement. If I take this and that, if I take inside the circle and outside the circle, I get the entire universe. This is a true fact. Now, in probability, U is our sample space. This is the universe of all possible things. So this means that I can think of S as the union of an event and its complement. And in fact, this means that the probability of S is going to be equal to the probability of the union of these things. Now, the probability of S is assumed to be 1 by our axiom. The probability of the union is going to be the sum of the probabilities because these guys do not have overlaps. A set and its complement are disjoint. So this means the probability of A is 1 minus the probability of A complement. This is an important equation. It's called the complement equation. And informally, basically what this says, the probability of what you want is the same as 1 minus the probability of what you don't want. Now, why is that useful? There are times when looking for the opposite of what you actually want is going to be a lot easier. And in such a situation, you can use this equation to find the probability of what you actually care about. By finding the probability of what you don't care about, if you know that probability, you'll automatically know the other probability. So that is going to be super useful. And I think at the beginning of the next class, I'll give you an example where you would see a use for that. Where we're going to care about something, but there are too many ways for it to happen, so you know what? Just pretend that doesn't happen. What's the chances now? Okay, I get that, subtract the answer from 1. And that's what we want. Let's kind of wrap up here. In summary, compute the probability of A. What you are going to do is 1, you're going to create a sample space. This is the first step. It is also the hardest step. This is going to have to be where you have to be a little bit creative. Now, of course, I'm going to talk about many situations, and we're going to be able to set up different kinds and thinking about when we can think about the sample space in what way with equally likely events. You are going to find the subset of SA. This is the event. 3. You are going to figure out size of the sample space and the size of A. That's going to be where you're applying all your counting principles. Does it matter? Does it not matter? Can we use combinations? Can we use permutations? Can we use the multiplication rule? Can we use something else? That's where all your counting is going to happen in step 3. And then 4, finally, the probability of A is going to be the size of A divided by the size of S. And by the time you get to step 4, you'll be able to do that. Now, certain formulas and strategies is going to save us from having to go through these 4 steps, but in principle, we're always going through these 4 steps, and whenever I introduce those strategies, I'm going to show you that we went through these 4 steps to even get there in the first place. But that is basically how the probability is going to work for us. And we'll start jumping into examples next time. So let's see